Thank you very much. Thank you for being here after the break. So this is a talk where I'm going to present a tool, but the tool's sort of not the main point of the talk. The main point of the talk is to try and get you to think about some aspects of reproducible research that I think have been have not been given enough attention by the community, and there's a lot of low-hanging fruit that we can all pick together. So this is a slide that I've used in a number of talks for far too many years because it hasn't really moved on. This is a survey that Nature did in 2016 asking people if they thought there was a reproducibility crisis in science, and people largely thought there was. This is a situation that had felt old by the time this came out. The original discussions around the reproducibility crisis sort of stemmed from a 2009 paper. But every year in Nature, there's another think piece about, what is AI doing for the reproducibility crisis? What is this doing for the reproducibility crisis? We sort of talk and talk about these things, but nothing really gets better. Over this same period, the demands on researchers continue to increase, the amount of statistical rigor, the sophistication of the software they're using, the concerns around data ethics and data governance that they've got to contend with, piling things onto them. But we're not improving the tooling that they're using to help make their research reproducible, and it's leading to a lot of disengagement from researchers on the ground compared to the sort of chitter chatter that we all do in this sort of community, saying reproducibility is important, let's do more. And so we sort of end up in this draw the rest of the owl scenario where we give people a 2-day software carpentry type thing saying, here's Git, this is great, this will help you do reproducible research. And then they go back and they try and get their 2 gigabyte file that's got sensitive data into it, distributed across all of their colleagues, and actually do these things in practice, and it all falls apart and they get really disillusioned. And I sort of want to ask, well, why are we still talking about it? Why is this still the same old conversation and so little movement in the tooling? And I think there's a number of reasons for this. One of them is that, objectively, people don't care that much, right? The pressure from the funders really hasn't turned up. It's a nice to have. It's not. You can do your whole career and not think about this and do just fine, right? But ignoring that social side, which is always dangerous, I think one of the reasons is people talk about different things when they talk about reproducibility. And it's used to sort of, I like this treatment out of the Turing book to think about the different ways things can be reproducible, right? So this breaks it down into whether or not you've got the same data or the same analysis. And reproducibility in a narrower sense is if you run the same analysis on the same data, you get the same answer. Seems pretty trivial, right? Generalizable is obviously a much bigger deal. This is someone's run a different analysis on different data and got the same broad conclusions as you. It's like, this is great. This is obviously like what we aspire to. And a lot of the replication crisis stuff came from this corner, right? But we've zoomed in as a field on this top left corner because it feels the most trivial, right? If you can't run the same code on the same piece of data and get the same result, like clearly it's all hopeless. We should just pack up and go home. And so I feel like we've ended up in a bit of a quagmire focusing on this box. And it's been, an enormous amount of tooling has happened to try and sort of build a Docker for research, like an environment that captures everything you might need so that you can definitely get bit for bit the same results that I get. And the reproducibility in this sense is you give someone a 200 gigabyte Docker container and say, like, there you go, it's all in there somewhere. But it hasn't really helped us advance things, right? There's other settings where this sort of reproducibility just isn't even what you want. I spend a lot of time working with people on stochastic modeling. I don't want them to have bit-by-bit reproducibility of their work, because if they get that, it means that they're playing around with random number seeds in a way that is likely to cause problems for their downstream analysis, right? We should embrace the fact that maybe different times you run an analysis, you get slightly different results. Ideally, that won't affect the overall conclusion, but this sort of nuance has been lost from like hitting things with a hammer and trying to get them to be as reproducible as possible when we interpret that reproducibility as running the same analysis on the same code and getting the same result. And so I want to suggest, perhaps somewhat as a hot take, that we focus on this box not because it's important, but because it's tractable. Right? We're tool makers, we build tools. You can do this, right? You can measure it and you can say, I've got a badge that shows you that I can do this. And so this metric becomes a target, right? It's notable that the other boxes in this grid are typically done by other people. right? They're harder to measure as a result. Different people coming in with different analysis and different data and trying to answer the same question as you. You can't put that in a GitHub action, right? So that happens organically, and we should try and set things up in such a way that enables that sort of corner to be as easy to do as possible. And so the whole thing is sort of it's all a bit wrong. And I feel like we build this idea of, I've stolen this meme entirely from Hadley Wickham, but we build this pinnacle of success. We think of reproducibility as a thing that happens at the end of a project. Have you climbed the pinnacle of success, and is your thing perfectly reproducible? And it's sort of as opposed to something you live. And it would be nice if we thought of it more of a pitch of success, a thing you can't help but fall into, right? The easiest thing to do is for your work to be reproducible. And that's what I think we should try and build as tools. And so the rest of the talk, after this rant is over, is about some of the steps we have taken to try and help do this. All right, so as a colleague of mine said on a recent grant, why don't we just Pareto the hell out of this? Like, what is the 20% that we can do that will give us 80% of the payback? What can we do by doing less? Right, so the ideas that we've tried to follow with this is just to think about the smallest amount of thing we could do to help with all the boxes in that reproducibility grid. How can we help researchers be confident about what went into an analysis, be confident what was a result of the analysis, and make it really easy to share and remix those bits of analysis with one another, and we can sort of build tooling based on that. So our solution for this is a package. It's an R package and a Python package called Orderly, but the ideas in this I want you to focus on rather than implementation, because we would love someone to come up with a better version of these sorts of ideas than us. We think this is sort of the first couple of iterations of this. The eagle-eyed of you will notice a 2 at the end of this URL, because we completely tore this down and rewrote this as we've seen how researchers have been using this. And I should say the context for this is my RSE group, who sit as an embedded group within a large group of computational epidemiologists. So we've been dog-fooding the ideas in this with our epidemiologists for the last 8 years. Right, so what I'm going to do is I'm going to show a couple of ideas that I think could go into any solution of this, things that I think are important to actually advancing reproducibility, and talk a little bit about how our tool helps with this. And the first principle is that analyses are always run more than once. We love it when we get PhD students coming in, and I'm just going to run this. I'm going to run it once, and then I'm done. This project's finished. And it's like, sweet summer child. So it would be nice if we could sort of put a box around that. And one of the things that we found really useful, just like the dumbest thing in the world, but has been an amazingly powerful idea, is when you run an analysis, just make a copy of everything, right? Disk is relatively cheap. Copy the inputs, copy the outputs, copy the whole shebang, stick it in a directory where they can't touch it, make it read-only. That is super useful when you come back later on and find out what did actually run, right? So you get this auditability of what was run. Ideally, and I know there's some metadata lovers in the room, this would contain some metadata, some information about what went into the analysis. I'm going to talk a lot more about that in a minute. So what we end up with is a whole bunch of little bricks, right? The 3 times that this was all run, 3 little identifiers alongside of it, each with their own inputs or outputs. So that later on, when you get a difference in your result, you can say, well, what was different? You know, was it that my data coming in was different? Was it the code I wrote was different? Was something about the environment different? And you can just build tooling against that later on, rather than saying every time I run this will be identical. So we're shifting this focus from can this be run again to this is what actually went in. And researchers find this a much easier concept to buy in. And technically, this is an awful lot easier to implement. So you can apply this to different boxes being different types of analysis, and we'll talk about this a bit more in a minute. One of these might be some data preparation. One of these might be some downstream analysis, right? So you're going to have some concepts here that we don't even really have words for about how we build up analysis out of little blocks. Okay, this next bit is about metadata. Analysis should know what they consumed and produced. But it also turns out that they actually kind of already know this, and a lot of the tooling that we give researchers to use, they're like, this is pointless because I'm just telling my computer things the computer already knows. And we've stolen a lot of ideas from Git around this. So on the left here, this is a fully working orderly script, ignoring the fact that it's pseudocode. So the researchers can write any old script they want, and it is immediately usable by this tool. Okay, and if you look at this, I've highlighted a couple of things on it. The script has got a name. It's called analysis.r. It's very imaginative, I know. And it's reading in a CSV file called data.csv. And along the metadata, which again I've just sort of displayed in a pseudo YAML-y sort of way, it's not how it's stored, we've recorded some information about that. So the hashes of these files are super useful. If you've got the hashes of the file, you can start asking questions like, did it change? Without having to go through and check all the files. But we already know what went into the analysis because we ran it, right? And we know what came out of the analysis because we ran it as well. And we've got copies of all of these things. So why are we getting the researchers to look after this? We can just monitor this as an analysis runs, right, in the tooling and store all of this potentially very useful information alongside of it. We know what packages they used as well because we ran the analysis. We can just ask the interpreter what packages have you got loaded at the end of this, and we can save all that information so that later on when they say, well, what was different about this, we can say, well, you ran it with these versions, I ran it with these versions. And rather than focusing on making things always do the same thing with the same versions, or always making sure everyone has to have the same versions, we can just explore those differences and find out, does our result depend critically on the version of NumPy that we're using? There's a whole bunch of other useful metadata that you can completely automate the collection of. And you just set this running in the background so when people run these analysis, all this stuff is saved. And then later on, if you need to use it, you can use it. Maybe you won't, but there's no cost on the user, right? Once they start using this, all this metadata will just come in for free. And so I said before, the Python version of this works exactly the same way. You run an analysis, it collects up all this metadata, it sticks it in a little JSON file, and you can inspect it later on. Python users do their work in Macs, I've noticed. So we've had a shift of focus that we've tried to we've explored a bit, which is moving from users should record what their inputs are to the tools should record what the inputs are. And then that means you can leave the mental bandwidth of the users to record the stuff that really actually mattered. What do they think was different? And that might be different to things that you can just automate pulling out of a tool. Okay, the next principle I think is really important is that tools should be progressive. A lot of tools in this space are super idealistic. They start off with grand ideas and they say, you need to buy into my whole vision in order to run Hello World. And we want to go the other way around and say, like, just bring us whatever you've got and we'll just make it work. And then later on, we can sort of build it up after. So like I said, this is a fully working script and people might start with this and then they might go, well, actually, I'd like to enforce this contract that I'm always going to produce a file called result.csv, and I want the analysis to fail if it doesn't. And I want to mark that this data.csv is a resource that has that I want to advertise that I will be using, so that we can start we can start tooling around how my analysis is going to fit together. And they can sort of opt into these things. There's a whole bunch of metadata they can sprinkle into their scripts that will turn on or off features, and they can, by default, get a long way without any of these, but as they buy into the tool, they can start using more and more of them. And we find this sort of human-centric approach has been really useful. And this is where having a captive group of a couple of hundred computational researchers is super useful, because you can find out what will fly and what doesn't fly, and what they're using and what they're not using. Right. Doing this by itself isn't very interesting. Where these things get interesting, and where I think the biggest conceptual gap in this field is in how these things plug together. Right? So the important idea here is that one person's output is another person's input. Right? Anything produced in one analysis could go into another. And typically the way we think about this is sort of like in a snake-makey, targetsy way of you have a computational graph that anyone can run, but we want to shift away from everyone has to run stuff and move towards you can just reuse what someone else has already run. And so in this framework, we have this way of declaring a dependency among these little data blocks, these little packets as we're calling them. Right, so you just declare, I want to use the latest version of the packet called analysis, and I'm going to use the file result.csv out of it. And that will take care of all of the grunt work of finding it and erroring if it's not there. It'll track the dependency back for you. And so then you can build a dependency tree backwards in time through what you actually ran, rather than one forward in time over what you proposed to run. And this sort of shift in how we see the graph has really helped us change the way we think about reproducibility. All right, so we're not trying to record what will be run when I run a thing, but what was run when I did run the thing, because it's that second one that really helps with reusing. All right, so what we want to do is build into a world where researchers can sort of have bits of analysis that plug and play like little Lego bricks, like the way we do with Docker containers, like the way we do with software packages. What is this composable unit of analysis, and why don't we have words for it? So that's, you know, if you do that on one person's laptop, that's great. You make a binder project, and you can do all that right now. But where the innovation in this has come from is can we think of this graph being distributed across different people? And so early 2020, all of our researchers suddenly got physically distributed as we were all forced to work from home. And we're working on an analysis of COVID data for the UK. We're getting data coming in, people are analyzing it, people are making onward simulations, people are writing reports, and different people are doing different parts of this work. It's a big project, it's running for a long time. And so we need to make it easy for the pieces of data to flow from one person's analysis to another, and have the two users who sat in opposite sides of London know that they're definitely talking about the same thing. And we know how to do this with Git, right? It's really, really easy. You just have this graph, you have these identifiers, and it just works. We don't really have this for data. And so the tooling that we've developed here sort of splits apart the metadata part of the graph and the artifacts, and allows all the users to have a view over the entire metadata graph, but not have to hold all of the data itself. And you can either centralize or decentralize where that data is being stored. But you allow the analysis to become distributed over people as well as over space. And this allows a really great new ways of collaboration. It allows you to do the same sorts of things you do with Git in terms of deciding, well, when will I adopt that person's breaking change in the code? You can do the same thing with the analysis. You know, someone's added a new variable to the model, and my fits that I'm trying to tune can't cope with that yet. So I'm just not going to pull that change in the data input in the same way that you might not pull that change in the code input. Right. So there's a bit of detail about this. It's sort of like, there's a subtlety in this graph that I think is really cool, and I don't think we're sort of still trying to work it out. That, you know, you draw a graph over these conceptual bits of analysis. Incoming data goes into fitting the model, goes into simulating some future, goes into a report of interpretation. But actually, the real graph are these concrete graphs between the individual packets, not between this conceptual piece of work. And this graph sort of, it exists in reality. It's not this hypothetical that you get with a workflow tool, right? You can just drill back through and say what went into. And the way people work with this, I think, is often quite different to the way that a lot of the data versioning thinking has gone on. You know, one piece of incoming data could appear in multiple model fits, but then multiple model fits might appear in one simulation, one piece of work simulating the future. So you can't just have like a single current version that you're keeping multiple copies of in a database, but only exposing one to the users. The users have to be able to work really dynamically with the artifacts stored in these graphs. And then finally, we've built a distribution layer to help with this. It is a web system called Packet that my group has developed. There's an API over that. So seamlessly with both the Python and the R implementations, you can be querying an API and pulling down copies of these packets of research data from central servers into your laptop as your analysis runs, and sort of helps make the whole thing really seamless. But you can also expose this to end users so they get a nice metadata-rich way of interrogating research outputs. So we've used this in a number of different contexts. It was developed initially for the Vaccine Impact Modeling Consortium, which is sort of a clearinghouse of vaccine modeling work held at Imperial. This is where we originally developed it for, and this is where our quite strict version was developed. And this was in response to a postdoc bringing me some work saying, here is a code I ran, and here is the result, and me looking at it saying, I can see that you're lying because the caption doesn't match up. And we're like, well, what can we do to try and just create a system where they can't help but not fall into that problem, so everything we send out ends up definitely being the results stored along the inputs for it. This COVID response was a massive scaling up of the ideas, and sort of it changed a lot of how we thought about distribution, how we thought about versioning, and how we thought about this flow across the graph. And this was massively collaborative. So we had 41 people working on the GitHub repository behind us with 15,000 commits on this. Some of these people who had never used Git before the pandemic. So we've ended up with 3.5 terabytes of data across about 23,000 nodes in this graph. So the whole system sort of scales up pretty well to complicated workflows, but also scales back down to individuals working on a laptop. Most of the people who are involved with this project now use this system for all of their work. And we're exploring this polyglot workflow where we're linking people working in R, making domain-driven models or fitting to data, with Python workflows where people are fitting machine learning models and using PyTorch and these really established stacks. And so by having a common and open spec for the packet metadata to be stored in, these two systems can just operate seamlessly on the same piece of data. So there's a lot of remaining challenges that we're still working through. The first one is sort of the most intractable, which is we're still trying to work out what is the right size of analysis. This is similar to when you start teaching Git to people at first, and they're like, well, what goes in a repository? Is it a package? Is it a paper? Is it like my whole lab's work? And there's no right answer to that, but there's a whole bunch of ways of working. Like, are you doing a monorepo style? Are you doing submodules? We've got language around that, and because we haven't even got language here, we're still really trying to work this out. People tend to go too small too fast. Disk is really cheap, like I said, but it still runs out, and it's very easy to use a lot of disk. And we solve this on the server end by using a lot of content addressable storage, which helps. It's difficult to preserve all the provenance information, which we're automatically tracking, but still allow users to safely share a subgraph. This is something that we're hitting when we start publishing results of this. If there's a point back in the graph that you want to hide from people because that contains sensitive metadata or sensitive data, we haven't worked out a way of making that workflow work seamlessly. And we've also found a lot of things that can go wrong when copying files, particularly involving network file system. The number of bugs due to file copying is really astonishing. And I just want to highlight here that you're probably looking at this and going, well, does Zenodo solve this, or Git LFS, or whatever? And it's like, yes, you're right. All of these ideas are shamelessly stolen from the tools that we have used, that we like, but sort of remixed together in a slightly different focus. And I think, as research software engineers, we need to start thinking this way. Like, what are the tools that our groups need, and just grab the bits from the tools that you like from a software engineering perspective and make them suitable for researchers to use. Stop telling them just hit the Zenodo API in your script with Python request library, and you can probably download the most recent copy and it'll work. Stop making them draw the whole out, and we should start building tooling that really helps them work that they want to work. Doing this, reproducibility doesn't have to be hard. You can build a culture where people expect reproducibility. One of the really neat things in working with this project and the researchers using it is after a few months of using this, it's like when people have used Git for a few months and they're just like, how did I do beforehand? Like, how did I cope? This is chaos when they go back to an old project. And so you can make them want reproducibility by bringing it to them in a way that's really digestible, but that also helps them, rather than saying, if you don't satisfy all of these criteria, your work isn't really reproducible and has less value. So in conclusion, I think 2024 is a really great time to be a research software engineer. It's, this conference is here now. There's a lot of us here. We'll talk about the same sort of things. There's a lot of really good low-hanging fruit. But I think some of it is quite unglamorous. And I think leaning into these unglamorous basic tools could have a huge impact. And so rather than chasing the next big exciting thing, perhaps we should just sort of look at how our researchers are actually working and try and remove pain points from them. I want to sort of appeal for people to make it as easy as possible for users to adopt your tools. If your README starts with handcrafting a JSON file or installing Nix or doesn't have Windows installation instructions, you're blocking huge chunks of your users, and it's easy to get into sort of a little echo chamber where you think everyone works the way you do, but research is a hugely varied group of people. I mean, you need to think about how they work. And try and design more humanely our tools and try and build pits of success so that researchers can't help but do the right thing. With that, I've got people to thank, my awesome team, and resources there if you would like to see our implementation of these ideas.
Thank you very much. So we've got Canopy, and I think we've got a couple of questions there already. I'll try to. get them up here. Are you going to just, okay, I'll just start asking Tom. Oh, that's a lot of questions. So when someone wants to rerun an analysis with the info Orderly has created, how do you avoid becoming a package manager to match versions?
We solve that problem by just not, to be honest. So part of this comes from our department is pretty R-centric, and the way that our package distribution works hasn't led to the sort of virtual environment lock file style of working with things. People just expect the top of the versions to work. So we've sort of punted on this problem with the idea that when someone comes to us with a concrete copy of it where they want to solve it, we'll use tools like RENV or whatever to build those. But as of yet, no one has said, I want exactly these versions of packages. So we're solving problems there that the researchers empirically don't seem to think are important.
Thank you. Oops, things are switching around. No, I needed to go back to newest. There we are. So Schwab was asking, a recipe not being updated in a while was an early version of something you are trying to do, I believe, in PyOrderly. It might be worth a quick look to see its take on it. So I think that's more a comment than a question.
I will do that.
We've got Sean asking, most of the examples were of scripts written by researchers. Has much thought been put into how this approach might be applied to applications not written by the researcher?
I'm not sure what applications are being hinted at here. Please. I can repeat it into the mic if you shout it out.
So I come from kind of like the HPC kind of background where instead of writing a script, So I come from a HPC background where instead of writing a script where you do some analysis and write out some kind of data files, what you'll often start doing is running a massively parallel simulation, and then kind of that will produce some data, and then you can work on the analysis there. So I'm thinking, has much thought been put into how you tie the initial big simulation to your data analysis afterwards?
It goes in the same thing.
It just works.
Yeah, so okay. we did exactly the same thing. The data analysis, the initial data processing would happen. The main analysis for that COVID response, small fry by a lot of HPC standards, but it's about a CPU year a day. So those we sent to our HPC, and then we pull the results back in. So the researchers could have a copy of the source repository for this checked out on their laptop, on the HPC shared server, another copy on another person's laptop, and they can just push and pull the packets in. So it becomes the way of provisioning the HPC to have all of the bits it needs. It then runs and writes out the files in its store, because the store is decentralized, and then you can pull it from there or push it up to a server. So it actually works really well in an HPC context.
Okay, thank you. So I very quickly try to get through some more questions. So if you can just very quickly answer. What are the pros and cons of this versus other workflow systems like Nextflow or SnakeMake?
We do not believe this is a workflow system, and we have tried very hard not to add any workflow features to it. What we'd like to do is make a plugin to let you use those workflow systems to drive the sort of implicit workflows here, but we haven't explored that route yet. Something like Nextflow, like they've spent a huge amount of time and effort on that system, and we have no desire to duplicate it. Our focus is on distributing these and addressing the outputs of each of the bits of the graph as first-class entities.
Oh, Nicholas seems to have a lot of questions. So if Nicholas wants to talk to Rich afterwards. Is Nicholas
in here or online? Oh, is he? Yeah, we'll definitely
Yes, okay. I leave the two of you, and I would ask one more question. How to make sure a workflow is still reproducible in 10 or 50 years? What happens if Microsoft decides to shut down GitHub in the near future?
I mean, none of this depends on GitHub, and I'd say that the thing that would help in 10 or 15 years is not being able to rerun the code, but just having a solid audit trail of what went into it. Languages change, packages change, compilers change. You may not be able to to boot up a copy of anything that can run this. But if you've got a copy of the code that definitely went into it, you're miles ahead of not having that.
Okay, thank you very much.